Balloon 44 Weather Theory and Reports. Let's explore the fascinating relationship between temperature and dew point, a delicate in the air that defines relative humidity. The dew point measured in degrees signifies the temperature at which the air becomes saturated and can no longer hold additional moisture. This magical convergence between air temperature and dew point results in the enchanting transformation of moisture into visible forms like fog, dew, frost, clouds, rain, hail, or snow. Now let's cast the spotlight on fog, an ethereal cloud that hovers within 50 feet of the ground. When the air near the surface cools to its dew point, water vapor undergoes a mesmerizing metamorphosis into the captivating mist we call fog. Fog, appearing in various types, owes its formation to the prevailing temperature and the amount of water vapor in the air. Fog, with its minute droplets of water or ice crystals, is akin to a silent storyteller in the atmosphere. Unlike clouds, fog lacks visible downward motion. It simply hangs in the air. A common weather hazard for balloonists, fog often lingers close to the Earth's surface. The base of fog meets the ground, setting it apart from clouds, which initiate their performance at least 50 feet above the surface. Notably damp and gray, fog poses challenges during takeoffs, landings, and in-flight, restricting surface visibility. Let's unravel the mystery behind fog formation. Picture a scenario where the relative humidity is near 100%, a crucial condition for condensation or sublimation. High relative humidity, achieved through processes like additional moisture evaporation or air cooling to its dew point, sets the stage for fog. Fog takes center stage when the temperature dew point spread is less than 1.1 degrees C, especially with a light wind creating a gentle mixing action. Every story has its nuances, and fog is no exception. In regions with industrial influences, persistent fog may occur thanks to smoke particles and sulfur compounds. As the relative humidity decreases, fog bids adieu. This decrease can be triggered by strong winds or heating processes. Now let's delve into some fog types and their characteristics. Imagine the Earth radiating back the heat it soaked up during the day. By early morning, as the surface temperature drops, radiation fog may emerge. It loves clear skies, high moisture content, and light winds. When warm, moist air flows over a colder surface, advection fog takes the stage. Coastal regions, especially in the southeastern United States, often witness this captivating performance. If advection fog forms over water, it earns the poetic name sea fog, dense and mysterious offshore and onshore. As we explore the magical realm of fog, we discover the intricate interplay between temperature and dew point, a choreography that brings these ethereal clouds to life. It's a symphony in the sky where every element plays a unique role in shaping the atmospheric narrative. As the evening unfolds, a captivating phenomenon known as valley fog takes the stage. Picture this: cold, dense air gracefully descends from higher elevations, winding its way into low valley areas. As it weaves through the valleys, accumulating coolness, the air temperature intimately interacts with the dew point temperature. While the higher elevations often bask in the clarity of the night sky, the valleys cloak themselves in a misty embrace, casting a veil over the landscape and limiting both ceiling and visibility. Now let's turn our attention to evaporation fog, a wondrous creation fueled by the addition of moisture to the air. There are two main performers in this foggy drama: frontal fog and steam fog. Frontal fog graces the stage in the company of slow-moving winter frontal systems. Imagine liquid precipitation gracefully descending from the maritime tropical air above the frontal surface, only to meet the polar air below. As the falling drops evaporate into the chilly polar air, they generously contribute water vapor, elevating the dew point temperature to match the air temperature. The cold air, now saturated, gives rise to the enchanting frontal fog. This fog loves to accompany active warm fronts throughout the seasons, typically manifesting about 100 miles ahead of the surface front. Often entwined with intermittent rain or drizzle, it might make an appearance as prefrontal fog or postfrontal fog, depending on its position relative to the warm front. Enter steam fog, a magical performance set against the backdrop of cold, stable air gracefully gliding over a non-frozen water surface that radiates warmth. It begins as intense evaporation transforms liquid into vapor, saturating the air and conjuring the ethereal beauty of steam fog. This enchanting display is commonly witnessed over lakes and rivers in the fall and over the ocean in winter, especially when an offshore wind adds its gentle touch to the choreography. And so, the atmospheric ballet continues, with valley fog and evaporation fog playing their respective roles in the mesmerizing theater of the skies. In the complex dynamics of the atmosphere, stability and instability play pivotal roles, influencing the behavior of air currents and shaping weather patterns. Imagine the atmosphere as an expansive canvas where stability acts as a steadfast force, resisting disruptions to maintain a calm horizontal flow. In contrast, instability introduces a lively rhythm of upward and downward movements, fostering turbulent airflow and convective activity. This delicate equilibrium between stability and instability defines the choreography of the skies. As air ascends, a transformative sequence unfolds. Rising into areas of lower pressure, it gracefully expands and cools, undergoing a metamorphosis. Conversely, descending air subject to increasing pressure warms with a comforting embrace. This adiabatic interplay, a rhythmic of heating and cooling, accompanies every breath of the atmosphere. Moisture, a whimsical partner in this atmospheric ballet, adds a nuanced dimension to the performance. Lighter than dry air, it beckons upward, initiating a harmonious ascent. Yet, in its descent, air becomes denser, embracing stability. The delicate interaction between moisture and temperature determines the atmosphere's temperament, ranging from the cool stability of dry air to the dynamic instability of warm, moist air. Visualize the natural flow of air as a horizontal symphony, marked by gentle breezes and graceful movements. In a stable atmosphere, disturbances quickly dissipate, yielding to the comforting rhythm of horizontal flow. Conversely, in an unstable atmosphere, these disturbances grow into a tempest, culminating in towering cumulus clouds and thunderstorms, an energetic display of vertical movement, lightning, and precipitation. Stability, the atmospheric resistance to vertical motion, hinges on the distribution of air's weight. Warmer air, lighter than its colder counterpart, rises, creating instability. Conversely, cooler air descends, seeking equilibrium, establishing stability. This delicate balance of light and heavy air determines the atmospheric stability. The canvas of stability unfolds in 5 acts. Absolute stability, where air resists upward movement. Absolute instability, where any lift prompts ascent. Conditional instability, a delicate between dry and moist adiabatic rates. Neutral stability, a tranquil state with no inclination to rise or descend. And convective stability, a scenario impacted by mechanical lifting. In this grand performance, stable air fosters cloud formations with modest vertical development, resulting in clear skies and serenity. Unstable air, on the other hand, orchestrates the creation of towering cumulus clouds, thunderstorms, and turbulence, a dynamic display of convective energy. As air subsides, a winter's embrace may bring inversion, intensifying stability. A lid forms above, trapping smoke and haze and leading to reduced visibility. This atmospheric symphony, a play of stability and instability, shapes the very essence of weather, creating a captivating spectacle that guides the intricate movement of the skies.